Episode 9 ended with a simple question. The controller may be asked to check the same object many times. This can happen because a previous attempt failed, the object changed again, or the controller restarted. But checking the same object again should not create extra pods or repeat the same action unnecessarily. So how does Kubernetes make repeated reconciliation safe? Let us begin with something familiar. Imagine a light is off. If the instruction says toggle the light, running it once turns the light on, but running it again turns the light off. The result changes every time. Now change the instruction to make sure the light is on. The first run turns it on, and every later run simply leaves it on. The same difference appears in Kubernetes. Create one pod is like toggle. If that instruction is repeated, another pod is created every time. Make sure 3 pods exist is different. The controller creates a pod only while fewer than 3 exist. Once the count reaches 3, repeating the check changes nothing. This repeat-safe behavior is called idempotency. The word sounds complicated, but the idea is simple. Run the same reconciliation once or run it several times. As long as the desired state has not changed, the cluster should end in the same correct state, without creating extra work or extra resources. This works because the work queue does not tell the worker to create the pod that was missing 5 seconds ago. It only gives the worker an object key, default /webapp. The key means, look at this application again. The worker must then read what the application wants and what the cluster looks like now. A reliable reconcile loop follows a clear sequence. First, read the desired state. Second, observe the current state. Third, compare the two. Fourth, change only what is missing or incorrect. Finally, report the new result. The next time the key arrives, the loop starts by reading again. Now let us run that loop. Web app A says 3 pods should exist. The controller checks the cluster and finds only 2. The difference is 1. So the controller does not blindly create several pods. It asks the API server to create exactly 1 missing pod. The controller sends that create request through the API server. Once the new pod is stored and becomes visible, the cluster now has 3 pods. The important point is that the controller asked for the missing result. It did not assume that every queue delivery must create something. A moment later, the same web app A key arrives again. This time the worker reads the desired count of 3 and the current count of 3. There is no gap. The correct action is to do nothing. That no-op is what makes the second pass safe. Notice what the worker did not do. It did not replay the old message that said 1 pod was missing. That message may already be out of date. Instead, the worker used the key to read the latest state. This is why Kubernetes reconciliation is based on the current level of the system, not on blindly repeating every past event. Now look at the dangerous version. This controller receives web app A and immediately creates 1 pod. It never checks how many pods already exist. A retry creates another pod. A second notification creates another. The controller started with 2 pods and accidentally ended with 5. The safe controller behaves differently. Every time web app A arrives, it reads the desired count and lists the pods it manages. It computes the gap using the latest numbers. If 1 pod is missing, it creates 1. If the count is already correct, it stops without making another write. Idempotency also applies to updates. Suppose the controller wants to mark the application ready. It should first check the current status. If ready is already true, Another update adds no value and may trigger another event. So a good controller writes only when the new value is actually different. The controller must also know which resources belong to the object it is reconciling. Web app A should count only the pods that it manages, not every pod in the namespace. Labels, selectors, and ownership information create that boundary. Without it, the controller may count the wrong pods or create duplicates. Controllers sometimes need to work with services outside Kubernetes. For example, a controller may ask a cloud provider to create a database. But suppose the request succeeds and the reply is lost because of a network timeout. The controller does not know that the database was already created. If it sends a completely new request, it may accidentally create another database. To avoid this, the controller should use the same fixed database name and first check whether that database already exists before creating it again. The same idea applies when something is being deleted. Before Kubernetes removes web app A, the controller may need to delete the database created for it. If the cleanup is interrupted, Kubernetes may ask the controller to try again. By then, the database may already be gone because the first attempt succeeded. In that case, the controller should not treat it as a failure. It should accept that the cleanup is complete and allow web app A to be removed. Not every failure should be handled in the same way. A temporary network problem can be retried because the reconcile loop is safe to repeat. But an invalid desired state, such as a replica count below 0, will not become valid just because we retry quickly. In that case, the controller should report the problem clearly instead of creating an endless retry loop. We can now turn the idea into a practical checklist. Start from the key. Read the latest desired state. Find the resources this object owns. Compare desired and actual state. Make only the smallest required change. Write status only when it changed. Then return, knowing that the same key may arrive again. We can now see how all the pieces work together. First, a change is saved through the API server. The reflector notices that change and passes it into the informer. The informer updates its local cache so it has the latest view of the cluster. Delta FIFO keeps the incoming changes in the correct order while this happens. Once the cache is updated, the event handler adds the object's key to the work queue. A worker then picks up that key, reads the latest state from the cache, and checks what action is still needed. Because it always starts from the latest state, the same reconciliation can run again safely. Let us end with a real production issue. At 2 in the morning, the team receives an alert. The checkout application is supposed to run 3 pods, but 5 pods are running. At the same time, they notice several other events. The watch connection was lost. The informer had to rebuild its cache. The same key reached the work queue more than once. An API request timed out, and the controller restarted. Some of these may be normal recovery behavior, while one of them may explain the extra pods. So which event is the real cause of the problem? This incident brings together many ideas from the earlier episodes. The API server had already saved the desired number of pods as 3 at resource version 800. Later, the watch connection was lost. Because the older change history was no longer available, the reflector fetched a fresh copy of the current state and rebuilt the local cache. After the cache was ready, the event handler added checkout app to the work queue again. The same key may appear more than once during this kind of recovery, and that by itself does not mean something has gone wrong. The evidence now helps us narrow down the problem. The API server still says that checkout app should run 3 pods. The Informer cache is fully up to date. All 5 running pods were created for checkout app. The work queue sent the same key 3 times, but that can happen during normal processing. The worrying part is in the controller log. It says that the controller creates 1 pod every time the key is received. That means the repeated signal is being treated as a repeated create command. Now we have to identify the real cause of the problem. Was it the API server, the missing old history in ECT, the reflector rebuilding the cache, the shared informer, Delta FIFO, the repeated key in the work queue, or the controller itself? To solve it, follow the complete flow we have learned across these episodes. Look for the point where the system stopped checking the latest state and instead treated every repeated signal as a new instruction to create a pod. In the next episode, we will trace this incident from the first change saved through the API server to the moment the 5th pod was created. We will identify which events were part of normal recovery, find the exact mistake in the controller, and then fix the reconcile loop so repeated signals no longer create extra pods.